Now it's time for us to discuss the various LAN hardware that we will find in the local area network of an enterprise LAN design. Some of this hardware that we're going to talk about, we definitely are seeking out a destruction or a elimination of these forms of network hardware. Let's go ahead and take a look at the hardware devices that we might find in a LAN. We're talking hubs, repeaters, layer 2 bridges, switches, layer 3 routers, layer 3 or layer 4 switches. We'll talk about the distinctions between all these particular titles and all of these particular devices. Hubs and repeaters. These are the devices that we are looking to eliminate from networks today. Why are we looking to eliminate them? Well, because they're layer 1 devices. They're simple physical layer devices. As a matter of fact, they're often referred to as bit spitters. Yep, good old-fashioned bit spitters, which are just taking in bits from one port and simply repeating those bits out all of the other ports. So we are definitely looking to do away with these devices on the network. But why? Really, I mean, why? What's the big deal with these bit spitters? Why are they so frowned upon? Well, the answer lies in the fact that they do not create additional collision domains for the devices that we are trying to connect over the local area network. So you've got these devices that connect to this hub, and when one of these devices sends a communication into the device, it is repeated out all of the possible ports of the device. This creates one big collision domain. One big collision domain. And that is the major problem with these devices. They do not create the additional collision domains that we want. I know it's a little confusing, but the initial or additional collision domains, they reduce collisions that are on the network. So it is fairly confusing, this terminology, but we've got to understand it. In order to reduce collisions or eliminate collisions, we increase the number of collision domains. We refer to these hubs and repeaters as unintelligent. Now, why we refer to them as unintelligent is because of the fact that they do not learn any addressing on the network. They don't have any intelligence when it comes to any layer or level of addressing. Oftentimes, these devices are unmanaged. We just plug them in, plug in the devices to them, and that's it. There's absolutely no ability to manage in any way, shape, or form this device. There are exceptions to that, but typically these devices are unmanaged. We said there's no intelligence. There's no learning of any information. Therefore, there's no inspection of information before the frame is forwarded. So, the device is very, very unintelligent. Remember, everything that connects to this device, like we said, is in its collision domain. Because collisions are possible between the devices must operate in CSMA-CD half duplex mode. Yuck. We don't like half duplex communications because this is inefficient. If we have a 100 megabit per second link, for example, and we are forced to operate in the half duplex mode, we're only going to get about 60% of that bandwidth for actually sending data. So we'll only be able to utilize about 60% of that bandwidth if we're forced to organize in the half duplex mode of communications. By the way, compounding this problem of all of the devices existing in the same collision domain, all of the devices are also forced to be in the same broadcast domain. So when one of these devices connected to the hub sends out a broadcast, everyone must contend with that broadcast packet. So there's no creation of additional broadcast domains. There's no creation of additional collision domains. And this is the huge problem with these devices. Layer 2 bridges and switches. Well, now we are adding intelligence to the devices that we find in the local area network. For sure, we're adding intelligence. By the way, what's the difference really between a bridge and a switch? Well, bridges are mainly used for media translation. Okay, they're mainly going to be used for media translation, and that means they're typically going to have a lot fewer ports. Okay? They're not needed, it's not a requirement for them bridges to have as many ports as switches do. Also, another key distinction between bridges and switches is the fact that bridges tend to be slower in their operation. Switches have those many ports, and they have specific hardware inside of them to do the particular job of forwarding and filtering traffic on the network. So we find that switches typically really outperform bridges in their operation. But it's funny that the two terms are often used interchangeably between bridge and switch, and that's because fundamentally they operate in the same manner. Notice we call them layer 2 bridges and switches because, surprise, surprise, they do indeed operate at layer 2 of the OSI model. That 7-layer OSI model, these devices operate at layer 2. We contrast this to the hubs and repeaters that we just spoke of that operate at layer 1. Notice most of these devices are going to be manageable devices. We can connect to them with Telnet or Secure Shell in order to configure, monitor, manage them. Many of them are going to offer graphical user interface alternatives for managing the devices. We know that we call the data and encapsulated header information that these layer 2 devices work with, we call these frames. And these frames are forwarded based on the layer 2 MAC address information that is encapsulated in the header of the frame. The table that is stored on the layer 2 switch for making these forwarding determinations is referred to as the content addressable memory table. We also call it simply the MAC address table. Notice that layer 2 switches that we're talking about are indeed layer 2 Ethernet switches, and that's our main focus in this class. But we do need to realize that certainly in technologies like frame or ATM, we have other types of switches that are utilized, but they do operate under the same logic, where they are tuned to be learning the layer 2 address information. Notice that layer 2 bridges and switches, they get off the hook when it comes to rewrites. They don't do operations at layer 3 by definition. So the layer 3 router is the one that has to worry about the encapsulation process. And of course, we know that the encapsulation process has to do with rewriting MAC address information. So switches are really hardware accelerated bridges. that have these specialized application-specific integrated circuits for really, really efficiently forwarding and filtering traffic frames based on MAC address information. Now, the beauty, the magic of these switches is our ability to do what is called micro-segmentation. Micro-segmentation is what we're able to do with these layer 2 devices. The micro-segmentation refers to making the smallest possible collision domains. That's what micro-segmentation refers to. Specifically, what we want to do is we want to create a collision domain for each device that needs to connect to the network. Each access layer device gets its own collision domain. This allows full duplex communications, and finally, we'll go ahead and achieve 100% of the bandwidth, for example, for sending traffic. Unlike half duplex, where we only had the effective utilization of 60 or so % of the bandwidth. So this micro-segmentation approach, taking devices and giving them their own collision domain, this is the magic, this is the beauty of our layer 2 switched environment. Notice by default, all of the devices that connect to the switch are in the same broadcast domain, but that's by default. We can easily change this through the creation of what we call virtual local area networks. So unfortunately, the default is for these devices to be gathered together in one broadcast domain, but this can indeed be modified through the creation of these VLANs. We know that by default, every device is in the same layer 2 broadcast domain, and that's because a broadcast frame is addressed for a very special MAC address. The special MAC address that is the destination MAC in a broadcast is all Fs. So when this broadcast frame is received, by default, it gets flooded out all of the ports on the switch. This is what we indeed refer to as the broadcast domain. And the one exception to this flooding behavior is the one the broadcast came in on. Very nice of the switch to realize, okay, well, if this broadcast came in this port, fast Ethernet 0/10, for example, obviously I don't need to turn right around and send it back out that port. Unfortunately, if you were to have a completely unmanaged bridge or a switch, you would be stuck with all of your ports in the same broadcast domain. But the good news is we, in Cisco networking, focus on manageable or managed switches, and these are going to allow us to configure virtual local area networks. Our virtual local area networks allow us to organize our hosts into separate or different broadcast domains. Within the same virtual local area network, we have efficient layer 2 switching going on. And then when we want to communicate between VLANs, that's when we bring in a route processor. That's when we need what's called the default gateway in order to route between these virtual local area networks. It's easy to remember that we need a router in order to route between these VLANs Because when you look at a VLAN like this VLAN 10 here, and then you look at a VLAN like VLAN 20, you realize, oh yeah, they're in different TCP/IP subnets. In Cisco's implementation of virtual local area networks, a TCP/IP subnet is another definition, if you will, of the VLAN. Notice each VLAN is its own TCP/IP subnet. When we see this fact, we realize, oh yeah, okay, that makes sense. When devices are communicating within the same VLAN, they don't need a route processor. The layer 2 switches can handle that. But when devices go to communicate across VLANs, a route processor is required. Notice in this case, a device up here, let's say, right here on the network, this device in VLAN 10 would communicate with VLAN 20 by sending the traffic into this switch, which would trunk the traffic. Let me draw this again here. So we've got a device right here in VLAN 10, and this device wants to communicate with a device in VLAN 20. It's going to send the traffic to its layer 2 switch. That layer 2 switch is going to trunk the traffic down to this switch, which will trunk it down to this switch, which will trunk it down to the route processor, the default gateway in this example. That default gateway will then go ahead and properly forward the data back into the infrastructure and send it into the appropriate device in this case, VLAN 20. So notice in this configuration, we've got several technologies working together. We've got our trunk links, and these trunk links are for carrying VLANs from Cisco device to Cisco device. And then we've got inter-VLAN communications that are occurring thanks to the existence of what we call an RP. We like to call it an RP, a route processor, because it doesn't necessarily need to exist anymore in a router. We have route processors in firewalls. We have route processors in multi-layer switches. Obviously, we have route processors in routers, but you get the idea. A lot of different devices can feature the ability now to route traffic at layer 3, and sure enough, any of those devices would be able to assist us with our inter-VLAN routing. Now, I want you to notice something that's interesting about this particular design. Notice the VLANs are built around the functionality in the organization. This actually isn't a common approach anymore. Notice here it's kind of implied that human resource employees, some of them are located on this switch, some of them are located on this switch, and some of them are located on this switch. And then a sales VLAN was created, and some of them were located on this switch, and this switch, and this switch. This is actually, it's a good depiction for our learning of VLANs, but it's actually a poor depiction for the real world implementation of VLANs these days. A better example would be showing them based on geography, okay? Because that's what's happening now. Like you would have your first, or this is actually the third floor, isn't it? So you would have your third floor east VLAN, for example, and that would be up here. So we are creating VLANs that are constrained to one switch closet now at the access layer, and we'll go ahead and create them based on geographic location. Notice that reduces right off the bat the amount of inter-VLAN communications that needs to take place. I mean, definitely you could still organize VLANs by function within the organization, but that is losing popularity, that approach. So we love VLANs, don't we, in our designs? Because we know they create additional and smaller broadcast domains. They help with security because now broadcasts are going to be constrained. And also, the VLANs really help us keeping a fault isolated. If some machine here in VLAN 30 malfunctions, typically the only machines that are at risk are those machines that are in that VLAN 30. So a lot of times the organization of your network into these VLANs can really help when it comes to fault detection, fault management. As a matter of fact, breaking your network up into VLANs can really help with the overall manageability of your network to begin with. So we know that these Ethernet networks definitely have scalability limitations because of that concept of the collision domain. The more and more devices you place in that collision domain, the greater chance there are for collisions and the less efficiently the CSMACD can function. Layer 2 switches, as we've talked about, what is so great about them is they segment the network into these collision domains on a per port basis. This is referred to as microsegmentation. Again, we're really emphasizing it because it is the beauty of these layer 2 base networks that we designed today. Now, we do have some scalability issues to address even with these lower layer 2 switches, because we do get into scalability problems based on the total number of hosts in a network and the total number of hosts that are going to be able to survive in a broadcast domain. Cisco says, you know what? You don't even want to consider getting up around 500 hosts in a TCP/IP subnet. Cisco says, you start to get to the 500 devices in a subnet thing. That looks like 600. Let me redraw that. So we don't want to get to anywhere close to 500 devices in a TCP/IP subnet because we're just going to definitely start to have problems even if we're in a layer 2 environment. Now, this CAM table, or otherwise known as the MAC address table, we know it's going to do forwarding based on destination MAC-based switching. One of the issues is, unlike the IP routing table that we've discussed a little bit, we can engage in summarization. So if you were to have 50,000 hosts in your network, you would have to maintain mappings for 50,000 MAC addresses. Again, no ability to summarize any of that information. How these switches work is to identify a layer 2 address and then to map that layer 2 address to a particular port. And here's the really scary thing. If this content addressable memory table fills, what happens? Well, our layer 2 switch starts acting exactly like a hub. It will not have the appropriate MAC address to port mappings for new destinations, and it will therefore flood those new destinations out onto the network. There are utilities to attack your layer 2 switches, like MAC off. This utility will come in and just fire false MAC addresses rapidly at your layer 2 switch to fill its CAM table and therefore to have the switch suddenly act like a hub. One of the great protections that we have built into our network is we know there's eventually going to be a layer 3 router in the mix, and that layer 3 router, by its very nature, is going to leave off these segments. It's going to make sure that broadcasts, for example, are not passed from one segment to the next. So we know that one of the things that we're going to do on these devices is address the huge broadcast domain issue. This will help us guard against things like broadcast storms, and it's the VLAN construction that will help guard against problems based on the size of our broadcast domains. Typically, the rule of thumb in Cisco, and we'll talk more about this when we design our IP infrastructure, but typically we're talking about one VLAN per /24 IP subnet. This means we've got about, 250 workstations maximum in one of these VLAN-based IP subnets. So our layer 2 switches are going to be great at creating the additional collision domains, but one big broadcast domain by default, unless we go in and we create our virtual local area networks. The layer 3 router, it's going to go ahead and separate things into separate collision domains, and it is also going to separate the networks with different broadcast domains. And here's where students typically have a question right off the bat. They say, all right, well, wait a minute. If we have a layer 3 router that is creating the separate collision domains and the broadcast domains, by default, why not use routers exclusively in our topology and skip this whole layer 2 switch thing? And the answer really comes down to cost per port. Yeah, we know that routers have relatively few ports, and it would be pricey real quick to add enough ports to our modular routers in order to enable them to be used like this at the access layer. So switches are the devices that are built especially for the access layer, and some switches we're going to find with a lot of ports, hundreds and hundreds of ports on the switch for very effectively and cost effectively getting devices onto the network. Something else that would be an argument against using layer 3 routers in this capacity is the fact that they do tend to be slower than some of these souped up layer 2 switches. Yeah, they can switch traffic from interface to interface, but they are nowhere near as efficient as the layer 2 switches are, because the layer 2 switches were built from the ground up just for that job. They were built from the ground up to do that access layer, layer 2 switching that we spoke of. We know that routers, they've got a bit more work to do, don't they? They are forwarding packets based on the destination layer 3 address. We'll focus on V4 and V6 addresses in this course. The router has to do 3 things. The poor router, it's so busy compared to the switch. The router has to take care of the actual routing decision. So the first step here is the router's got to figure out the actual routing decision. It has to look into its routing information base, known simply as the RIB, and it's got to figure out what is the best way to get to a destination. And that's routing information base RIB, not RIP. Then once the router figures out where that traffic's got to go, it then engages in a switching function where it figures out between which interfaces it has to pass the traffic and actually engages in that traffic passing. And then finally, the router has to worry about encapsulation. The router, unlike the switch, has to worry about that layer 2 header rewrite. For example, it's got to take the source MAC address, remove it, and replace it with its own source MAC address. So there's rewriting that has to be done in the layer 2 header, so we can see the 3 jobs. And this is without talking about security and quality of service and other jobs that the router can have. Just the routing process alone does occur over a sequence of these 3 phases or steps. Now, the most exciting device that we have is what I just simply call multi-layer switches. Some people will make the distinguishing characteristics between a layer 3 switch and a layer 4 switch, but I like to go ahead and just handle this whole issue by referring to anything that's a switch that understands above layer 2. If it understands above layer 2 and it's a switch, I just go ahead and generically refer to it as a multi-layer switch. In fact, I find that almost all Catalyst switches sold now that are non-layer 2, so they're multi-layer devices, they can all understand above layer 3. So the multi-layer switch title is a perfect title for these devices. Obviously, the magic of these multi-layer switches is they have layer 3 routing intelligence built in. They also still have the layer 2 intelligence with those hardware accelerated application specific integrated circuits that make them lightning fast at actually switching traffic, unlike a Cisco router. By the way, the ability to switch traffic really fast has evolved over the years with these Cisco devices. Initially, everything was process switched, which was relatively slow and involved, the frame comes in, it's stored, and then it's examined, and the forwarding decision is made, and all of this was done with software mechanism. And then they invented fast switching, which used a caching approach in order to speed things up. And then they invented net flow switching, which was previously called multi-layered switching, also known as route once, switch many. And now what they've invented, the latest technology, is the Cisco Express Forwarding switching. This is on by default on just about any Catalyst switch you would see these days. And what this is it's taking that routing information base that had existed in software on the multi-layer switch, and it's renaming it the forwarding information base, and it's putting it in the device's hardware for faster operation. Think of it like a pre-built cache. Instead of caching traffic on demand as packets are being attempted to be sent to locations, this particular Cisco Express forwarding approach is going to move traffic based on a pre-built table or cache of information. So, Cisco Express Forwarding is the latest switching technology on these devices that allows for blazingly fast performance. This gets in what we were talking to you about earlier. This gets into wire speed type performance. Able to switch the traffic at blazing raw wire speeds. Again, multi-layer switches today, they can literally look at not just layer 3 addresses. When routing first entered the switches, it was limited to just layer 3 routing decisions. But now we know that switches can look at like TCP, UDP, source destination port info. They can even incorporate this into the Cisco Express forwarding. They can do better optimization of traffic forwarding based on this information. These layer 4, if you will, switches can do more and more sophisticated security mechanisms. And again, I like to avoid this whole debate of, well, exactly what type of a switch is it, by just categorizing switches as either layer 2 or I just call them multi-layer if they can do more than layer 2. And you'll find that just about every catalyst switch made these days can do more than just layer 2 and layer 3. They do understand higher levels of the OSI model. All right. So, routers, repeaters, layer 2 switches, multi-layer switches, all ingredients that we can find in our networks. And I think we've covered what you would need to know about these various devices for the CCDA exam. By way of review, let's go ahead and name at least 3 benefits provided by virtual local area networks. What would be at least 3 benefits provided by VLANs? Yeah, pretty easy. I remember that we would have additional security as a result of these VLANs. The main thing, though, that I think of right away is the additional broadcast domains that we can create to add to the efficiency of the network. And I also love the fact of how it's going to be much easier for us to prevent and catch faults in the campus network when we have these nice segmented broadcast domains. All right, great stuff. Let's go ahead and grab a 10-minute break, our last break of the day. And when we return, we're going to go ahead and take part of our next module. We'll do part of the next lesson, wrapping up this module. And what I want to talk to you about is the different types of campus LAN designs and models that we can encounter out there. We'll talk about, actually it's a pretty short lesson, so I'll tell you what we'll do. We'll go ahead in the next chunk of content, we'll go ahead and finish up our module 2. That'll set us up in great shape for in tomorrow's sessions. We'll go ahead in day 3 of CCDA and we'll pick up with chapter 3. So we'll go ahead when we return and finish this second module on the campus local area networks.